All right, thank you. Good evening. My name is Obi Anamnachi. I'm a contractor at Anant and have been for about 9 months. And thanks for joining us tonight for Intro to DSE Graph. Today we're going to be talking about DataStax Enterprise Graph and the way that we're going to do that. Our schedule for tonight. We'll go through a short introduction. We'll talk about graph theory so that we can later compare to DSE graph and see what matches up and what doesn't. We'll talk about the specifics of DSE graph, and then we'll do a demo walking through a DataStax provided studio notebook um, for DSE graph. If you have questions at any time during the presentation, you can put them in the chat and I will try to get to them either during good stopping point or at the end. We'll have time for questions then as well. So starting off, DSE Graph is a part of the larger DataStax Enterprise project. It is a graph database. You can see an example of it in the picture over on the right, where pieces of data are represented as nodes on the graph. It's compatible with a lot of the other functionality that DSE provides, specifically analytics nodes, which are about using Spark, and also their search nodes built on Solr. It has a lot of the same advantages as using Cassandra normally. DataStax Enterprise is very much built on top of Cassandra. And their non-graph database functionality functions via Cassandra. Both Cassandra and DSE Graph are distributed scalable systems. If you bring up a bunch of DSE nodes and connect them together, you can use Graph and Cassandra and store that data across the entire cluster. And then both Cassandra and DSE Graph have high-speed transactions. In Cassandra's case, specifically for read, writes, updates, deletes. They're all very quick, and it's very similar for DSE Graph. You can insert nodes, remove nodes, all that very quickly, although traversing the graph itself is a little bit slower just because it's a more complicated type of operation. All right, going into graph theory. So graph theory is a branch of mathematics or computer science or algorithms or a larger field like that, that is specifically about the description and analysis of this object, a graph. Graphs are objects that are composed of vertices and edges. Vertices, they're just simple containers. They can hold data or they can hold nothing. And then edges connect vertices together and define the relationship between them. So you can see the top picture here is a general graph. The nodes are labeled A, B, C, D, and E, and they're connected by edges. But graphs are a very general data structure. There are a lot of other types of data structure that can be made to fit a graph model. Like you can see here, I've included a picture of a linked list and a picture of a binary tree, both of which can be described by the same graph rules. They have their nodes, they have their edges that connect them. So graphs have various types. We're going to talk a little about their taxonomy now. But the first thing to understand is that graph edges can be undirected or allow movement in both directions. So you can go from one node to another or back along the same edge. Whereas in a directed graph, edges only allow movement in a single direction. So that double-headed line you can see over on the bottom right is actually two edges, one that points from the bottom node to the right node, and one that points from the right node to the bottom node. It would count twice for the degree of a node is how you would say that in graph theory terminology. Degree is just generally how many edges are connected to a node. So some other definitions for the taxonomy of graphs. A simple graph does not have any loops or duplicate edges. You can have a simple graph that is directed and a simple graph that is undirected. A multi-graph can have duplicate edges. So you can have two edges connecting the same two nodes, but still does not allow loops. A pseudograph can have both duplicate edges and loops, but when you are counting the degree of a node that is part of a loop, the edges that compose the loop count twice. A mixed graph can contain both directed and undirected edges. So in a mixed graph, a undirected edge still counts for a degree of 1, while 2 directed edges are a degree of 2. And a fully connected graph, every node is connected to every other node by at least one edge. So if you space your nodes correctly, they form these geometric shapes. So a triangle is a fully connected graph. And if you have a square, as long as you have edges going along both diagonals, that's also a fully connected graph. And as you scale out the number of nodes, the number of edges increases via some specific mathematical formula. Yes. So a little bit about graph traversal is how I would say it, but we're going to talk about traversal in DSE graphs in a little bit, and that's a separate thing. But the ways that you can, I'm still going to use the word traverse because I don't quite have a better one to put here, but the way you can traverse a traditional mathematical graph is you have a start point and you have an endpoint, and it's the way that you spread out from your start point, going only to nodes that are adjacent to nodes that you have already explored in order to find the endpoint. And there are actually 3 or more ways to do this, but the 3 that can apply to any situation are random search. So you start at a node, you have all of the neighbor nodes or sibling nodes in a list somewhere, and you pick randomly the next one to go to. You add its adjacent nodes, and then you pick again. And you do that until you find the endpoint that you're looking for. Obviously, that's not very efficient because there's no upper bound on the amount of other nodes that you might go to before you pick the actual node. In a breadth first search, the search searches sibling nodes first, which means that hierarchically, at your starting point, all its adjacent nodes are sibling nodes to the first node, but nodes that do not touch the first node are not. So a breadth first search will search all of the sibling nodes first. It uses a queue of nodes. So it's first in, first out. Any node that gets put into the queue is searched before nodes that are put in after. So the way that works is you search in a ring around the starting node, essentially. So it's efficient when you're searching for things that are close to your starting point. And if you have a large number of branches or no very long chains. A depth first search, on the other hand, searches your child nodes first. So the first node, all of the adjacent nodes. So a child node of a node is one that is further down the path from the start. So what a depth first search will do is it will go down a very long chain, backtrack, and then search the rest, backtrack one space, and then continue going down so that it goes as deep as possible first, and by the time it gets back to the start, all of the nodes in that first path have been searched. And the implementation for this usually uses a stack, which is first in, last out. So when new nodes get added, they are the next ones that get searched. And then you can also, by applying various metrics to your nodes or edges, implement various types of best first search, which use some other metrics to determine what nodes they're going to search. Specifically, a very famous one is A star, which can find the shortest path by applying cost or distance to edges. Okay, so DSE Graph specifically is a graph database or a property database, which we'll talk about why that is later. It is made of vertices and edges, just like your mathematical graph. In DSE Graph, all of your edges are directed. You cannot make undirected nodes, but you can have two nodes going in opposite directions, connected to the same two nodes. In fact, you can have any number of edges connected to the same two nodes, which makes it a multi-graph. In DSE Graph, both vertices and edges can have properties, which are just a key value store. You define a schema for that key and value. You provide a schema for the value and associate it with a particular key. And properties can also have properties. So the main things that are being connected to each other in a DSE graph are properties. They also do all the data storage for your graph. And then besides properties, both vertices and edges have labels, names, and unique IDs. And we will see that in action in the demo, which will start now. So for this demo, we're using a Dockerized implementation of DSE, which includes DSE Graph. It is brought up with the Docker Quick Start terminal and accessed via Kitematic here. But what it does is it brings up DataStax Studio. Let's go back to this general. So these are the default notebooks for DataStax Studio. If you bring up an implementation without any extra configuration, you'll get these notebooks. Specifically, if you have volumes that you are replacing, then these notebooks will not be here. So we connect this to our DSE implementation. You can see that's done here. We have it connected to DSE rather than localhost. In this case, they're not the same, but if you're using DataStax Studio on Linux, they could be, whereas Mac would also be different and you'd have to connect it manually. All right, so once you have DSE up and running as well as DSE Studio, you can configure for development, which allows, it's very similar to allow filtering in your Cassandra tables. It forces the development environment to perform queries even if you would get warnings on them otherwise. First thing that we're going to cover is count. The way you access a graph with DSE Graph uses the Gremlin query language, but the way you call it in the first place is g.v. And then you can then add count to the end in order to get a count of all the nodes in your graph. Currently, we do not have any because we have not created any. And this is a problem that I had that I still have not been able to fix. It's a problem, I believe, with the virtual machines that make up this DSE implementation. If I try to run a node that's specifically using the analytics engine, so it would be running all our operations through Spark, it just runs forever because there's the problem with the virtual machine is that there's no build space. So Spark workers, Spark jobs aren't being built properly. So they'll just run forever and cause errors. And then we also cannot do this part because always on SQL service is not enabled. This is done by, you can enable always on SQL via messing with the DSE.yaml file. But since we don't have access to Spark in the first place, there's really no use. So there may be in the blog post that will come up on blog.anant.us concerning this. There may be screenshots from a Linux version of this demo where we run through all of those examples as well. So getting to the part where we create our first graph. So the first thing we're doing is setting a schema for certain properties. So you can see schema.property key person ID. So the property that we're creating has the key person or person ID, and it's a type integer. We also create one for name, gender, person, name and gender, and then we create vertices of type person with a person ID, a name, and a gender. And then we're adding a vertex to our graph. It is about Julia Child because we are using recipe books, the authors, their recipes, and their ingredients in order to form this graph eventually. But we add the vertex, we determine the label, and then also the properties associated with it, person ID, which we set to 1, name, which we set to Julia Child, and gender, which we set to female. When we run this, we can see in the table view that there is one node. It has the correct label, the correct person ID, and then it also has gender, name, and label here. If you look at it in the graph view, there is a single node. Here. By the way, I don't know if I mentioned this yet, but this language that we're using is called Gremlin. It's a query language for working with graphs. And when we talk about traversals in a little bit, that will also all be Gremlin. So this is creating our second category. This is a category for books. As you can see, it adds the properties of book ID, publish year, and ISBN. And in table ID, you can see that these are being filled out. So this is when we created our first edge. We have connected Chef Julia Child, the person, to, what is it, The Art of French Cooking, I believe, the book. Let's make sure. Yes, The Art of French Cooking, Volume 1. So as you can see in our full graph view over here, we have person. If you hover over it, you can see the types of data that are involved. And then our edge doesn't have any properties associated with it. You can see it has the edge label authored to indicate that this person wrote this book, but there are no properties associated with that yet. You can put properties on edges as well, but that is not being done here. All right, so this is technically our first traversal. What we are doing is we are checking for the person node with the name Julia Child using the has function. As you can see, it gives us back our single vertex, Julia Child. You can add a value map to the end to see the actual text representation of that object. It tells you the properties and it tells you their value. You can also get use the traversal step values to get a particular value. So this is all the values for the property name, but both book and person have the property name, so you'll get both of them. You can also use has label as a traversal step. By the way, all these traversal steps are stackable. So G.V gets you your normal full list of, well, G.V gets you your full list of vertices, G.E gets you your full list of nodes, and you can then use various traversal steps to filter that data down so that you're getting the exact data that you want out of the query. Okay, so we're going to start over a little bit with a full version of the graph. What we're doing here is we're just defining all the schemas that are going to be necessary, all of the properties, all of the property keys and types that are going to be necessary to use in this graph. And then we're creating all of our vertices and labels. And you can see we now have a more complete graph here. As you can see here, right here, there are two edges created that are going from one node to another. And you can have duplicate, well, they're not duplicate edges because they have different labels. But two edges can go from the same type of object to the same type of object. What we're doing here is we're adding all of our properties to the correct nodes and edges. We can also get it to tell us everything it knows about the schema. And you can also use traversal steps to cut down on the results from schema.describe. You can add things to a graph schema that you can then later drop. And then we can fill out our graph fully with a bunch of new vertices and edges. As you can see, DataStax Studio also has the utility for viewing your graph in full, vertices and edges. And it also has this nice legend here at the bottom. So now we get an actual use of g.v.count, which counts all of the vertices that exist in your graph. As you can see, it's taking a little bit longer now than when we had no vertices. And part of that is just the resources available to this virtual machine, which are not very much because I need to be able to run all the stuff for this presentation and the virtual machine on the computer at the same time. Well, we'll just move on a little bit, talk about traversals while that runs. So we already talked about has, which cuts down based on a particular property and vertex type. So in this case, has person named Julia Child means you're looking specifically for a person vertex with the property key name and the property value Julia Child. You can also then filter or traverse based on where your edges go. So in this case, you define the same vertex, the person node with the name Julia Child, and then out E means outgoing edges labeled authored. So if you ran this, you would get, I believe, a a list of all of the edges outgoing from that particular node, the one for Julia Child. You can also do in edges, and you can also do in V and out V, which are for vertices that are connected to those ingoing and outgoing edges. And there are various other traversal steps that you can add on to get what you want. But the point is that you're taking your full set of vertices or edges, you're filtering down and traversing along the graph in order to get the data that you actually want out. And that is what we're in the demo for today. If you have questions, put them in chat now. But in the meantime, this has been Obio Marimachi with Anant Corporation. If you would like to contact us, you can do so at solutions.anant or at the phone number listed below. What are some real-world examples of using Graph? So there are actually quite a lot of data storage implementations that might want to use Graph, but a very particular one, both for graph databases and the mathematical object graph, is social network mapping, where it's very important that you store not only your customers or the people involved themselves, but also their connections to each other and to other entities. Yes, it's a very good way to store all of the different types of relationships that people might have with each other through different types of edges. And it's a way of keeping all that data available, so that you can say, put up your Facebook users friend list or something. I don't know for sure that Facebook is using graph implementation for that. It's possible to just store it in a normal. How much space do you need for 50,000 social connections? I could not necessarily say. But as you've seen, properties are not huge things unless you have a lot of data to store in them. And then the vertices and edges themselves also are not very big. So the problems with space in graph databases would come when you have a huge number of nodes, which, I mean, it's something that people often use graph databases for. But all in all, it's a pretty efficient, it's pretty space efficient implementation. Would I recommend using DSE Graph over trying to do a man? You mean to keep track of a social network in Cassandra versus using DSE Graph? I would definitely recommend using some sort of graph database for that. I don't necessarily know if it will be more space efficient, but you would get more power out of graph traversals when working with social networks than trying to do the same thing with normal Cassandra filtering. Yes, DSE Graph is standard with DSE implementations. It's one of the options you can set when you're first bringing it up alongside analytics, which is Spark, and search. we actually sort of have an Intro to Spark webinar, um, specifically for replicating relational database joins. One is by Arv Mattel, which you can find on the YouTube channel or on blog.anant.us. But it might be worth doing an Intro to Spark one anyway, if we can cover more sorts of topics. All right. If there are no more questions, thank you for watching and have a nice rest of your day.